Our home, the planet Earth, is more than 4 billion years old. We often think of the Earth as unmoving and solid. In truth, most of the processes that are continuously shaping our planet are so slow and gentle that we hardly notice them. Sometimes, we are witness to some of the most violent stirrings of our restless Earth. Hi, I'm your host, Lourdes Carale. Welcome to the telecourse for elementary science teachers. In this episode, we shall learn how and why our planet is constantly changing as a result of geological forces. But before we start, let's review last episode's lesson on the atmosphere. Question: what are the layers of the atmosphere? Answer: these layers are the troposphere, stratosphere, and ionosphere. The ionosphere is divided into the mesosphere and thermosphere. Question: what are the different factors that affect the weather? Answer: air temperature, air pressure, humidity, wind speed, wind direction, and the amount of precipitation or rain are factors affecting the weather. Question: what is the greenhouse effect? Why is it a serious environmental problem? Answer: the greenhouse effect is the warming of the Earth's atmosphere caused by greenhouse gases such as carbon dioxide. If the global temperature continues to increase as a result of increasing amounts of greenhouse gases, grave ecological consequences are predicted to occur. Melting of glaciers and polar caps, flooding of coastal areas, stronger typhoons, and desertification of some places. By the end of this episode, you should be able to answer the following questions. 1. What is isostasy, and how does it explain why the Earth's land masses are not flat? 2. What is continental drift? 3. What is plate tectonics? 4. What are faults and how are they created? 5. Why are volcanic eruptions sometimes very explosive? And 6. How are earthquakes measured? Join us for today's lesson on the Restless Earth after this short break. Welcome back. In the quest to understand the forces that shape the Earth, one of the most important concepts developed by scientists is the principle of isostasy. Simply put, this principle states that the movements of portions of the Earth's crust can be visualized as a block of wood floating in water. When the crust neither rises nor sinks, this means it is balanced between rising and sinking. This balancing act is called isostasy. Isostasy explains why the thick but lightweight continental crust stands high in relation to the ocean basin underlain by thinner but heavier oceanic crust. Different portions of the Earth's crust float at different levels depending on how big and how dense they are. The Earth's crust is not one solid piece. It is cracked into a jigsaw of several huge pieces called plates. Because these continental plates float, not only do they rise up and down, they also slide over the hot molten interior of the Earth. This sliding motion, which happens very slowly, is called continental drift. This demonstration shows how the continents have been drifting over millions of years. And with us is Mr. Edmond Rosales. Edmond?
Okay, I have here a jigsaw of about 7 continents, and about 250 million years ago, these continents used to be lumped together as a single continent called Pangaea. As time goes by, very slowly, different continents move slowly For example, this is the American continent together with the South American continent drifted, and Asian continent moved this way while the Australian continent moved this way. And here we see the African continent, and this one represents the European part of the European continent, and lastly this represents part of the Antarctic continent.
So this is how the continents look now.
Yes, at present you will see that this is the Indian continent, Indian plate, which collided with the Asian plate, where we find the Himalayas. And here represents the Australian part, where part of it later became the Southeast Asian countries.
And is it true that the continents are still drifting slowly?
Yes.
Until now?
Until now, especially at the Himalayan mountains, every year the Himalayan mountains are still growing a few centimeters every year. Not only this, part of the North American plate, where we find the San Andreas Fault, part of the United States later will be drifted away from the mainland US.
Okay. Thank you very much, Edmond, for that information. What about the Philippine archipelago? Can the drifting of continental plates explain how the Philippines was formed? And why is the ocean so deep, just off the eastern coastline of our islands? To explain this is to understand the cause of continental drift, the spreading of the seafloor. New crust is being made all the time on the seafloor. Hot molten rock bubbles up through huge cracks between the oceanic plates. In other places on the seafloor, the plates slide over each other. As one plate overrides another, the other plate slips down into deep trenches like the Philippine Deep, reaching depths up to 9 kilometers. Often, the hot mantle along the trench reaches the surface, giving birth to volcanoes. The Philippine Islands were probably formed by ancient undersea volcanoes in this way. The concepts of continental drift and seafloor spreading were recently unified into the theory of plate tectonics. This theory proposes that the lithosphere is broken into a number of moderately rigid plates. Depending on how they move compared to the plates next to them, we can define three kinds of plate boundaries. There are zones of divergence where the plates move away from each other. There are zones of convergence where the plates move towards each other. And there are transform fault boundaries where the plates slide past each other. We have with us Mr. Rolly Rimando, a geologist from the Philippine Institute of Volcanology and Seismology. And Rolly is here to demonstrate to us an activity about faults. First of all, Rolly, what are faults and how are they formed?
Faults are a reaction of the crust to the various stresses or pulls and pulls that it is subjected to.
Yes. And what are the different kinds of faults?
There are three basic types of a fault. The first type is normal fault. Then you have a reverse type of fault. Then a strike-slip fault.
Could you show us, using these models, what these different faults are?
We're going to use these models to illustrate the formation of the three basic types of fault. This is a styrofoam model, and the colors represent the layers of rock that the plates are made of. In a normal type of faulting, one block moves down relative to the other, and you see how the layers of rock are displaced by normal faulting. Now, if this block that moved down moves up instead, then you have a reverse type of faulting. Now, for the strike-slip type of faulting, we're going to use this model. And there's a diagram of a stream to illustrate the effect of a strike-slip faulting. In strike-slip faulting, one block moves past another block. So what happens is that this block moves either to the left or to the right, this way.
Yes, and you can see the effect on the stream, isn't it? So when it moves that way, there is what do you call that? Dislocation?
Displacement.
Displacement. There is displacement of the stream, and also when it moves the other way, there is also displacement of the stream.
That's right.
Okay. Thank you very much, Rolly, for these demonstrations that our teachers can do in their own classrooms. When we return, we are going to learn more about faults and about earthquakes. Please stay tuned.
This time, Mr. Rolly Rimando will tell us about the Marikina Valley fault system. Rolly, how many faults, major faults, are there in the Philippines?
There's one major fault in the Philippines. It's called the Philippine Fault Zone. It's composed of many splays or branches, and it stretches from northwestern Luzon up to Davao for about 1,600 kilometers. Of course, there are other faults, like in Metro Manila, we have the East Zambales Fault, then we have the Lubang Fault, and of course the Marikina Valley Fault System.
What prompted PVolts to research on the Marikina Valley fault system?
Okay, long before we knew that there was a nearby fault system near Metro Manila, we thought it was a good idea to study that fault and its activity, a fault which is right in our own backyard.
How long is this fault and what areas does it traverse?
The fault system is at least 120 kilometers long, and it extends from north of Bulacan, that's near Nueva Ecija, through east of Metro Manila and up to east of Tagaytay.
What are your findings so far, and what are the implications of these findings?
Our research findings show that the Marikina Valley fault system is active and quite active, and that the fault system moves every 200 to 400 years. The implications of these findings is that people should be prepared no matter when the next earthquake is going to occur, whether it's going to be tomorrow, next month, or next year. It doesn't really matter. The important point is that people should be prepared. People can do a lot to prepare for an earthquake, like they could adopt a personal preparedness measures before, during, and after. Like before an earthquake, they could do a lot to within their homes to prepare, like stabilizing objects that can topple, aparadors, and stabilizing ceiling fans, preparing medicine kits, those things. Also, during an earthquake, the most important thing is not to panic, because if you panic, that's the end of it. What do you do? Instead of panicking, people can duck under a sturdy table, for example, near the doors, stable areas. And also, after an earthquake, people can also do a lot. Like, how do you exit? How do you go out of the building after the earthquake? You don't go out of the building during the earthquake when there's a strong shaking, because you don't have much time anyway to go out. You'll just cause panic and possible stampede. So do the exiting after the earthquake.
Thank you very much, Rolly, for the useful information that you have shared with us. We hope you have learned much from this interview. Erupting volcanoes are only a small part of the Earth's volcanic activity. Much of the molten rock or magma rising from the Earth's mantle never reaches the surface. When it rises beneath continents, it cools slowly and hardens underground, forming many kinds of igneous intrusions. Once again, we have Edmond Rosales here who will show us how rising magma can be simulated inside the classroom. Edmond?
Okay, we have here cooking oil, a small plastic vial, glass jar with water. First, we put some oil inside this plastic vial. Take note that the cover has a small hole. Okay. And this cooking oil represents our magma, while the water represents the crust. Watch closely as I submerge and gently squeeze the container. Here, you see oil form some bubbles.
And the bubbles rise to the surface.
Yes. And the bubbles rise up to the surface of the water. Our magma forms bubbles that floats to the surface, where they may join together to form bigger masses of cooling magma called an intrusion. Each rising bubble represents a giant globule of igneous rock called a pluton.
Of course, igneous intrusions don't explain why some volcanic eruptions are so explosive. Underneath a volcano, rising magma is trapped. As magma rises, gases present in the magma begin to swell, creating a buildup in pressure. This pressure forces the magma through narrow tubes and bursts out on the surface in a violent, explosive eruption. Earthquakes are ground vibrations caused by fault movements, volcanic eruptions, meteor impacts, or movements of magma underground. The origin of the vibrations is called the earthquake's focus and is located underground, up to 700 kilometers deep. The point on the surface directly above the focus is called the epicenter. There are two general classes of earthquake waves. There are body waves which travel through the crustal material, and there are surface waves which travel along the surface. The strength of an earthquake is measured in terms of intensity or degree of destruction, as in the modified Mercalli scale, and its magnitude or amount of energy released, as in the familiar Richter scale. Over millions of years, glaciers have gouged valleys. Rivers have carved great canyons. Wind and rain have sculpted cliffs, and water has changed the minerals inside rocks. Only a few centuries ago, a new force has begun reshaping the earth in new and substantial ways. People have cleared forests, interfered with rivers, terraced steep mountainsides for farming, and built strange new mountains. People have become so numerous, using machines so powerful that they have become a kind of geological force. But unlike natural processes that take millions of years, human activities take near decades to create impact. And this either makes him a worthy overlord or a very real danger to this, our restless Earth. I'm Lourdes Carale. Join us next time for another episode of the Telecourse for Elementary Science Teachers.